Okay, welcome back. This is video 2 on the topic of fancy adding. In video 1 at the end, where we got to was the description of a hard problem, or what looks like a hard problem, a sum from k equals 1 to n of a times r to the power of k minus 1. And to make it look less weird, we can put some particular numbers in, like if a is equal to 3 and r is equal to 2, and our n is equal to 100, we'd be looking at what's a fast way to calculate the sum from k equals 1 to 100 of that, of 3 times 2 to the power of k minus 1, which is 3 times 2 to the 0, plus 3 times 2 to the 1, plus 3 times 2 to the 2, all the way up to 3 times 2 to the power of 99. What's the fast way to do that? Okay, so this is our goal. I want to figure out how to add this quantity up. I'm going to start the same way. I'm going to say S is equal to a times r to the 0 plus a times r to the 1 plus a times r to the 2 plus a times r to the 3 plus, well, maybe that's too many. I'll just do that. Then dot, 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 plus. Okay, let's leave a space, leave another space. Now let's think about what the last term is going to be. The last term is going to be k replaced by n, so a times r to the n minus 1. Now, what's the second last term going to be? We're going to have a times r to the n minus 2. And what's the third last term going to be? It'll be a times r to the n minus 3. We're just reducing our k value by 1 each time as we work backwards from the end. Now, unlike the proof for the summation of the first n integers, I'm not going to prove the summation formula by reversing the order of the sum or changing the order of the sum in some way. Instead, I'm going to calculate, for reasons that are maybe hard to see right now, r times s. I'm going to take the s expression and multiply it by r. So we'll have a times r to the power of 0 plus 1, exponents add, plus a times r to the 1 plus 1, plus a times r to the 2 plus 1, plus dot, 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 plus a times r to the n minus 3 plus 1, plus a times r to the n minus 2 plus 1, plus a times r to the n minus 1 plus 1. So I'm multiplying each of those by r. And I should write down something here that b to the n times b to the 1 is b to the n plus 1. Just a law of exponents. Next, so not at all like what was done for the previous proof. Instead of adding both expressions together, I'm going to subtract them. I'll subtract the first one minus the bottom one. And what we'll get is on the left-hand side, we have s minus r times s. On the right-hand side, we have ar to the 0. I'm going to add them. I'm going to subtract them in pairs. Minus ar to the 1 plus, now we have the next pair, ar to the 1 minus ar to the 2. I'm just going to do a little bit of highlighting so it's easier to see which ones are what. Like this is that one. That ar to the 1 plus 1 is the ar to the 2 that's being subtracted there, because we have another ar to the 2 that's not that one. Ar to the power of 2 minus ar to the power of 3. I'll highlight that as well. So that ar to the 3 is this one. Just color coding is helpful sometimes, making sense of this. Okay, and then we have the plus. Let's see. Dot, dot, dot. I'll continue down here. Plus ar to the n minus 3 minus ar to the n minus 2 plus ar to the n minus 2 minus ar the n minus 1. Do some more color coding. Let's see, I got my green, my yellow. I'm running out of good highlighter colors. I guess I'll go with blue. So this one here is coming out of, where is he? This one, that one. And then let's say I use the blue, the green, the yellow. Gotta go with the red. So that one is this one here. Okay, and then the last one, the last pair, plus AR to the n minus 1 minus AR to the n. And I think I'm out of good highlighter colors. Running low, I guess I can use the orange. So this one is that one there. So remember, we're subtracting the bottom from the top. So that's where all those subtractions came from. Now look what happens. Something awesome. We have an AR to the 1 with a minus and an AR to the 1 with a plus. They cancel. We have an AR to the 2 and a minus AR to the 2. They cancel. Now you can guess, or you don't have to guess, you can figure out that there's an AR to the 3 and an AR to the 3 that will cancel. An AR to the n minus 3 and an AR to n minus 3 that came before that will cancel. So all these middle terms are canceling each other. We'll cancel that and that. Cancel that one and that one. And what we're left with is just the first term and the last term, because nothing canceled with those. So we have s, common factor out s from the left, so s times 1 minus r equals AR to the 0 minus AR to the n. So s times 1 minus r is equal to a times 1 minus r to the n. Then I'm going to divide both sides by 1 minus r. And that's the proof of the summation formula for the geometric series. It's a standard proof. You can find it in almost any calculus textbook. You'll find it in the appendices of textbooks in finance, actuarial science, sometimes stats. So summation formula for geometric series. Just as a warning that sometimes the sum starts at 0. Sum from k equals 0 to n of AR to the k. So there's different ways that summation formulas can be indexed. I won't bother you with that. I'll let that be a topic that's described in the courses that do that type of thing. Shift the index around. So it's a shortcut for adding up some number of terms. You can imagine if there were thousands of these, it's way better just to use this one-off formula than to add up 1,000 of something, even if each individual piece is easy to get. There's a whole bunch of these, as mentioned, a whole bunch of different summation formulas. The one that was just proven is at the top left, so the geometric series formula. The one that's below that is the one we started with. So I'll remind you about that. This says it's the sum from k equals 1 to n of c, where c is a constant. It's not a function of n. So what this is like is the sum from k equals 1 to n of, let's say, 3. So it'd be 3 plus 3 plus 3 plus 3 n times, which is like 3 plus 3 plus 3 10 times, which was 3 times 10, except it isn't necessarily 3, it's some number c, and isn't some number 10, it could be some number n. So instead of 3 times 10, it'd be c times n for the most general case. We have the summation formula from k equals 1 to n of k, which we already proved was n times n plus 1 over 2. And then the sum from k equals 1 to n to n of k squared, which I did not prove. I just stated that the shortcut for that sum is n times n plus 1 times 2n plus 1 over 6. So this, I'm going to add a little comment here. This is like 3 plus 3 plus 3 10 times is equal to 3 times 10. In the blue box are two properties, and both of them hopefully have some intuitive aspect to them. The first property says that the sum of a constant times a function is a constant multiplied by the sum of the function. So I'll explain with a concrete example why that should make sense. Let's say you have a function that describes how much money you make each day for 10 days. And your total amount of money that you would make over the 10 days would just be the sum of the money you'd make each of those 10 days. So day 1 plus day 2 all the way up to day 10. But what if your pay was to be doubled each day? How much money would you make? Well, you could repeat the sum. You could do 2 times your pay on day 1 plus 2 times your pay on day 2 and do that all the way to day 10. So double each of the day payments, then add them together. Or smarter would be take the answer you already have. We already added up the pay for each of the 10 days and multiply that by 2. And that's all that formula is saying. You can take a constant out of a sum. Now the formula below that says that you have the sum from k equals 1 to n of two terms of two types of functions, f of k plus or minus g of k. And this property says that we can rewrite this sum as the sum from k equals 1 to n of just the f part plus or minus the sum from k equals 1 to n of the g part. We can add up each part of the sum separately and then add the results together. So I'll give you an analogy for that. Let's say you got 2 jobs. You work 4 hours in one job. Let's say you work 5 hours a day in the other job. And you get different pay for each of those jobs for each of those days. If you wanted to know how much were you paid in total over the 10-day period, you could do that 2 different ways. You could take the amount you make each day from both jobs and add that together. And that would be your pay on day 1. Do the same thing for day 2, day 3, and day 4. So now you have a new function that is a combination of the pay from both jobs. And then add up the amount for each of the days. That's method 1. Method 2 on the right-hand side, you could take your first job and figure out how much did you make from that job in the first 10 days. Then take your second job and add up how much did you make from that job in the first 10 days. And then add both numbers together. And you have to have the same thing at the end. It shouldn't make a difference how you add up those things. And that's all that rule is saying, that you can split up a sum into 2 sums. Or you can work backwards. You could take this expression on the right and turn it into this expression on the left, which is usually the way it would go. I'm going to show you some examples of using these summation formulas. And there's a mysterious connection that will be made between the examples I'm showing you here and the next topic in the course. So this question in part A asks us to determine and simplify the sum from, or 1 over n multiplied by the sum from k equals 1 to n of 2k over n. So I'm going to do a few things. First thing is just to make a comment that k is the variable. And everything else is a constant. I'll put constant in quotes because this is even to be true if there was an x in there. As far as that sum is concerned, the only thing that we would treat as a variable is the index itself, is the k value. So in the next line, what I'm going to do is I'm going to use this property, the first property from the previous slide, that the sum of a constant c times f of k is equal to c times the sum over f of k. So I'm going to take the 2 and the n that are inside the sum and factor them up front. So 1 over n times 2 over n times the sum from k equals 1 to n of just k. Okay, next line. I'm going to simplify the front, the top times top, bottom times bottom, so 2 over n squared. And then, what's the sum from k equals 1 to n of k? Well, we have a formula for that. Formula from the previous slide as well. Sum from k equals 1 to n of k is equal to n times n plus 1 over 2. So I'll put that in the box here. N times n plus 1 over 2. And we can simplify a little bit. I can cancel the 2's top and bottom. And we're left with n times n plus 1 over n squared. Okay, part B asks us to do the same calculation. And after we do that calculation, this is a blast from the past. Something you would have done in your previous calc course is limits. This is a limit to infinity. So we're going to take the expression we got at the end, the 1 over n times the sum from k equals 1 to n of 2k over n, the expression we just simplified, and then examine what happens when n becomes infinite. So limit n approaches infinity of the answer that came out, n times n plus 1 over n squared. I'm going to simplify the top by distributing that multiplication. So n times n squared. N times 1 is just n. Next, I'm going to use a fraction rule. A plus b over c is equal to a over c plus b over c. Think about that backwards. If you had something like 1 over 10 plus 3 over 10, the denominators are already the same, so that would be 1 plus 3 over 10. Just add the tops together. We're just doing that backwards, running that backwards. That's where that fraction rule comes from. So if we use that fraction rule, we're going to have the limit as n approaches infinity of n squared over n squared plus n over n squared, and then that can be simplified. N squared over n squared is just 1. N over n squared is just 1 over n. Now this instruction, limit to an infinity for n, means we're replacing n with a gigantic number, larger than a trillion or a gazillion, whatever that means. And to think about what that means, let's think about dividing by progressively larger numbers, like 1 divided by 10. If you crack out a calculator and plug that in, you'll see the answer is 0.1. Do 1 over 100, calculator tells you it's 0.01. 1 over 1,000, 0.001. So what's happening here is that the number gets smaller as you divide by larger and larger numbers. So 1 over infinity, well, what's that going to be? We're going to move the decimal place over an infinite number of times. So 0.000000, and you just keep going forever. For all practical purposes, if we never stop pushing the decimal over, there's no difference between what we would get and 0 exactly. You could also think of this as a lottery. So imagine there's a million lottery tickets and you're holding one of them. Your odds of winning are 1 in a million. You know that's not good odds. And if there are a billion lottery tickets, your odds would be 1 in a billion. And you know that's worse odds. Well, 1 in infinity is extremely terrible odds. Your odds are 0. You're not going to win. Now that's a little bit counterintuitive because we're not used to dealing with infinities, but that is the truth. Okay, so I'm going to use that result here. Oh, and by the way, this limit as n approaches infinity is an instruction to do something to n. This 1 in front has no n in it, so it stays as 1. Just like if you have a constant, say f of x is 2 plus x squared. What is f of 7? Well, it's 2 plus 7 squared. Now, you don't plug 7 in for the 2, you just leave it alone. Same thing's happening here with the 1. You don't replace 1 with infinity, it just stays as 1. So 1 plus 0. We get 1 as the answer. So that's the answer for part B. The limit of that weird expression with the sum is equal to 1. You'll see later why it's such a neat question and what it's connected to. Okay, and then one more set of problems. Part A asks us to determine and simplify the sum from k equals 1 to n of 4 times 1/2 to the power of k minus 1. So I'm going to make the comparison to the sum from k equals 1 to n of a times r to the k minus 1, which is equal to a times 1 minus r to the n over 1 minus r. So with our particular a and r values, so with a equals 4 and r is equal to 1/2. So I'm just going to use that formula, replace the a with a 4, replace the r with 1/2. So there we have it. I'm going to do a calculation. 1 minus 1/2 is 2 over 2 minus 1 over 2, which is 1/2. So we have 4 times 1 minus 1/2 to the n, all over 1/2. Okay, in the next line, I'm going to use a fraction rule. If we have a divided by 1/2, or I'll make it more general than that. If we have a divided by b over c, we can change that into multiplication by c over b. So you can change a division into multiplication by the reciprocal. So dividing by 2 is the same as multiplying by 1/2. Dividing by half is the same as multiplying by 2. So if we use that rule, we'll get 4. Oh, color coding is a bit off. We get 4 times 2 times 1 minus 1/2 to the n. So we're going to get 8 times 1 minus 1/2 to the n. We can't do anything more than that. That's where we stop. Okay, part B. Determine the limit. Oh, put the n in the wrong spot. Determine the limit as n approaches infinity of that object. So this is the only new part. The rest of it's the same. So what we'll do is I'm going to replace that expression with what was found in part A. 8 times 1 minus 1/2 to the n. And we're going to let n go to infinity. So 8 times 1 minus 1/2 to the infinity. And I think, well, what does that mean? What does 1/2 to the infinity mean? Okay, so what does 1/2 squared mean? Well, that means 1/2 times 1/2, which is 1 over 4. What does 1/2 to the power 5 mean? That's 1/2 multiplied by itself 5 times, which is 1 over 32. Let's multiply everything out. 1/2, so this is smaller, right? As we're going from 1 over 4 to 1 over 32. We're dividing by a larger number, so we're going to get something smaller. How about 1/2 to the power of 1,000? That's really small. We're just going to write equals smaller. If you multiply 1/2 by itself more times, you get something smaller because multiplying by 1/2 is cutting it in half. Half of a pizza is a quarter of a pizza. Half of a half of a half of a half of a half. So cutting something in half 5 times will give you 1 over 32 of a pizza. Cutting something in half 1,000 times is going to give you very small pizza slices. What if you take a pizza and you cut it into a half an infinite number of times? How big is each slice? Nothing. So 1/2 to the power of infinity is 0. So we get 8 as the final answer here. And again, you'll see later on that there is a neat connection between these calculations, these types of sums, and limits of these types of sums, and the topic we're going to explore next, which is the opposite of taking a derivative, doing what's called integral calculus, or taking antiderivatives.